We have an outdoor unit PCB with us for repair. The complaint is that the outdoor unit is not working, and after 10 to 15 minutes, the indoor unit's display starts showing an E1 error. So the customer had initially taken this PCB to another workshop for repair. As you can see, the optocoupler is missing here, and they didn't reinstall it. Apart from that, if we look at the physical condition of this PCB, it is in excellent condition. There's no visible damage. The backside of the PCB looks almost new, and no work has been done on it so far. However, since it's come to me from that workshop, it seems they only worked on this optocoupler, but they couldn't fix it, so they left it as is. So now, let's repair it and see what the problem is. When the PCB shows an E1 error, it usually means either the PCB isn't functioning at all, or if it is working, then it indicates that the communication circuit isn't operating correctly. There could be various situations causing this issue. For example, if its capacitor swells, sometimes it might still be working, but the voltage isn't stable or proper, which can lead to this error. However, since we need to check the entire PCB, the first thing to do is power it up. But whenever a PCB comes to the workshop, we should always start by checking its fuse and high side components. This way, if there's any issue, we can catch it right there, repair it first, and then proceed to the next stage. So first, I'll check the fuse. This PCB has a single 20 amp fuse, so let's test it. The fuse is in perfect condition and is working properly. Besides that, it's essential for the PTC sensor to be in good condition because the electricity first passes through the PTC sensor, then goes to the unit and activates the SMPS system. After that, the microcontroller powers on, and finally, the switching relay is activated. Now, I'll test the PTC sensor by setting the multimeter in resistance mode, since the PTC sensor's value is measured in ohms. Here, I'm getting a reading of 46 ohms. If the PTC sensor's value goes above 200 or 300 ohms, it indicates it may be faulty. And if the value reaches kilo ohms, it means the PTC sensor is completely damaged. So right now, it's showing around 46 ohms, which means it's perfectly fine. If the value were higher, it would indicate a potential problem that could cause voltage drops. When resistance increases, the voltage drops, which prevents the system from functioning properly. Now the next step is to check the high side. Here we can see that a resistor has been removed. I'll check what component this resistor is connected to. This suggests that work has already been done in this area, so I'll need to check the diagram to verify what component this is and what should be installed here. Now, when I check this, I found that an optocoupler is installed here, which is responsible for providing feedback for the SMPS. The missing resistor I showed you earlier, which fell off, is supposed to be a 330 ohm resistor, and that's also missing. In addition to that, the optocoupler is also missing from this section. Before replacing the optocoupler, let's check the high side, because even if we replace the optocoupler, if there's an issue in the high side circuit, the PCB still won't power on. Now the high side here is very important, so let's check it first. To do this, I have set the multimeter to diode mode. Now we will check each component here step by step. When electricity passes through the PTC sensor, it enters the bridge rectifier, where the AC is converted to DC. Now, let's check the bridge rectifier. Place the positive probe on the positive pin and the negative probe on the negative pin. The voltage drop on the multimeter on this polarity should show for a short while and then disappear. As you can see, it showed voltage drop and then disappeared, which indicates it's working as expected. After this, let's check the next points. There should be no reading on any of these points, which means everything is fine. Now, let's check by reversing the polarity. Voltage drop on the first pin is fine, okay on the next pin too, and okay on the last pin as well. This confirms that the bridge rectifier is working properly. Now let's test the diode and IGBT installed in the system. If we talk about testing the diode, the system works in a way as shown in the diagram I've made. So it works like this. Points 1 and 3 are the common points, and the diode is connected to point 2. Now, let's check if it shows the correct readings. I'll turn on the multimeter and check in diode mode to see what it shows. As you can see, on both the outside points, the multimeter should show 0, indicating that these are common points. This is the expected result. So now let's check its cathode side. When we move from anode towards the cathode, we can see that it's absolutely fine. In the same way, we'll check the other point as well. Moving from the anode to the cathode, we can see that it's absolutely fine. When we check in reverse polarity, moving from cathode to anode, the reading appears and then disappears. This means that if we connect it the other way around, there shouldn't be any value showing. This indicates that the diode is perfectly fine, with no faults in it. Now, after this, let's check the IGBT. We should see the voltage drop on these pins. One point, 220 voltage drop is shown on this pin, which is fine. Now let's move on to check the IPM. First, let's check the positive and negative by placing the positive probe on the positive and the negative probe on the negative and see what it shows. There should be no value displayed, and as you can see, no value is showing on any point. Now, we will reverse the polarity of the probes. At this point, we should see some value, which will appear in the form of voltage drop. Here, it's showing 0.459 volts, so we should continue to see a similar value going forward. If any point shows 0, it means the IPM is faulty, and in that case, you would need to replace the IPM. So, all the points on the high side are perfectly fine, and there are no faults in them. This means that we should change the optocoupler here, provide electric power to it, and check its voltages. Now, the optocoupler and the resistance have been newly installed. As you can see, I've installed the 816 optocoupler, and in addition, I've also replaced the resistance because it was missing. Additionally, here you can see that I've installed a new optocoupler. The right side is an 816 and the left side is an 815. The voltage speed of both optocouplers is different, so if you use the same type, it will work properly. However, if you use a 917 or another type, it might not work correctly. This is a technique to ensure compatibility, so it's better to use the same part to get optimal performance. However, if you check the datasheet and then install it, even if it's a replacement, it should still work. But checking the datasheet is very important. Now, the PCB is completely fine. We will install the line and neutral. The center terminal is the line connection. The adjacent one is for neutral, this one is for the signal, and the last one is for the earthing connection. I will now supply the electric power. As soon as I supplied the electric power, you can see that the light is flashing, which means the unit is now completely fine. I was planning to test it in the unit, but I recently spoke with the customer, and they mentioned that we didn't check the wires since the unit wasn't working. I have suggested to them that they should replace the wires completely, and after that, I'm hopeful that the PCB will be perfectly fine. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.